Welcome, thanks for signing in today. Like I said, my name's Amy. I'm a product marketing specialist for our developer and DBA tools here at Redgate Software. I'm here in Cambridge in the UK with my colleague Richard Mitchell, who's product manager for our Oracle tools at Redgate. Say hi, Richard.
Hello, everybody.
So yes, and just to let you know, obviously you can see our contact details on the screen if you need to get in touch with us after the webinar. I'm going to just say a quick few things before I hand over to our presenter today, Randolph Geist. He'll take you through his session, and then we'll be here to help answer any questions at the end. We'll also be sending around this session via email to anyone who's attended today. So hopefully that will be useful if you want to go over anything after the webinar. So just a little bit of information on Redgate Software if you're not aware. So we design what we like to think as highly usable and reliable tools that solve problems which are commonly faced by DBAs and developers. Our tools are used by 600,000 technology professionals worldwide, including 93% of Fortune 100 companies. And our suite of Oracle tools consists of Source Control for Oracle, which helps you take the complexity out of recording schema changes in your existing source control system. We also have SQL Compare for Oracle, which enables you to compare and synchronize schemas, deploy changes from source control, and automate for continuous integration. And then Data Compare for Oracle, which enables you to compare table data quickly and generate update scripts without writing a single line of SQL. For more information on Redgate, our tools, and to learn more about Oracle itself, you can visit red-gate.com/oracle or our Oracle community site, allthingsoracle.com. The allthingsoracle.com website sees about sees about 35,000 visitors per month, and we have about 18,000 people signed up to our monthly newsletters. So hopefully people are finding it really useful. The aim of it is just to provide a gateway into a wealth of information and material for Oracle developers and DBAs, hopefully like yourselves. We work closely with a lot of the leading people in this field to deliver really unique content through the site and to showcase articles and resources that can be found on many other Oracle-focused blogs and websites. Content including webinars like this one today. Which leads me over to our presenter today. So Randolph Geist has been working with Oracle software for about 20 years now, and since the year 2000 he's been working as a freelance database consultant. So he focuses primarily on performance-related issues, and in particular in helping people to understand and unleash the power of Oracle Cost-Based Optimizer, or CBO. So he blogs about CBO and performance-related issues, and also regularly contributes to the official OTN database-related forums. He's a regular speaker at all of our all major user conferences around the world, and he also acts as an instructor for the Oracle University as part of their Celebrity Seminar program, where he gives seminars on advanced Oracle performance troubleshooting and mastering parallel execution. He's also a proud member of the Oak Table Network and the Oracle ACE Director Program. So, after all that, without further ado, I'm going to hand over to Randolph, who is going to present our session today. So just bear with me while we swap over screens. And like I said, if you've got any questions throughout the webinar or when we've finished, just pop them into the questions box that you should have on your screen, and we'll get to them afterwards. And also just don't forget that, I think most of you have, but just make sure you mute yourself throughout the webinar. So I'm just going to change presenters and hand over to Randolph.
Okay, so hopefully you can see my screen and hear me, so that would be good to know if someone could just confirm that. Okay, great. Right, so thank you, Amy, and welcome here from the southern area of Germany. I live close to Heidelberg, if that tells you something about the location where I'm currently am. My name is Randolph Geist, and welcome to my Exadata in-memory real-world performance presentation. I'm 45 years old and have a 15-year-old son, and as Amy already said, I'm independent consultant focusing on performance-related issues. I'm also co-author of Expert Oracle Practices and also co-technical reviewer of Expert Oracle SQL, member of the Oracle ACE program, and also member of the Oaktable network, but this has already been mentioned by Amy. So what I'm going to talk about today is a very brief introduction into Exadata and in-memory. Then the real-world case this all here is based on that I encountered at one of my customers. We will then have a look at various query profiles and what they do to this secret sauce features of Exadata and in-memory. Then based on this analysis, I will come up with a couple of ideas how things could be further optimized, and we will wrap up things with some lessons learned from this. So let's start with this Exadata introduction. So Exadata is part of Oracle Engineered Systems, so that means you get hardware and software both from Oracle, and the basic architecture of the system is that you have so-called compute nodes which run the standard Oracle software that you know and that you can also install, of course, on non-Exadata systems, so there's no difference in the software that runs on these compute nodes to the standard Oracle database software that you know. And in addition to these compute nodes, there is the so-called storage grid, which consists of these storage cells, and these storage cells and the compute nodes are all linked together via this InfiniBand network. So so far this is nothing too special. So these storage cells contain, of course, the actual storage, the spinning disks that contain and hold the data. But the special thing about the Exadata architecture is the software that runs on these storage cells, this so-called cell software, which makes this storage an intelligent storage. So this storage is able to understand the data that it stores, so it can actually read the blocks, can understand the contents of this database blocks, and can then perform certain functionality of a SQL execution already in these storage cells. So the secret sauce of Exadata in principle is that it is capable of distributing the SQL execution work between the compute nodes and the storage cells. So some parts of the execution that typically in a normal Oracle environment takes place on these compute nodes can be offloaded, as it's always called, this offloading. It can be offloaded to the storage cells and can already be performed in these storage cells. So this offloading is also called smart scans. So you can have in Exadata these smart scans which already can perform the filter evaluation during these scans and can also do the projection, so which columns you select. This can also be performed in the cells. Furthermore, there are these so-called Bloom filters, which are an optimization for joins that filter. So rather than doing the filtering during the join evaluation, these filters can already be evaluated during these smart scans, which further reduces the amount of data that then needs to be shipped to these compute nodes. Then there is this so-called storage index technology, where these cells maintain a minimum and maximum value for certain columns, for certain storage regions, which allows these smart scans to evaluate during a scan whether a certain storage region needs to be read or whether it can be skipped. So that's another optimization that these smart scans can perform, so that some storage regions might not even be processed during these smart scans, which can further speed up the smart scan speed. And then Exadata allows this so-called hybrid columnar compression. So data can be compressed in a very efficient way, and these compressed information can already be decompressed in the cells during these smart scans. So all of these things, there are more things, but these are the most important ones. All of these things can already happen during the smart scans within the cells, and this has, of course, then two advantages. First of all, you distribute the processing, so you make use of more CPUs and cores that are available in the storage cells, and it reduces the amount of data that needs to be further processed in the compute nodes for the further processing, like joins and aggregates, which will then be performed in the compute nodes. Furthermore, we have PCI Flash cache in these storage cells, and these support all kinds of read and even write operations. So by default they support caching of single block reads, multi-block reads, and even speeding up redo log writes, so you can speed up log file sync, commit operations, and optionally you can configure this flash cache even to be a write back cache, or you could even specify that a particular table space should be completely reside on this flash cache. So all these things can be configured and are again just a measure to speed up the I/O. Yeah, and in the most recent releases of Exadata, this means quite impressive scan speeds. So on uncompressed data, you can reach scan speeds, if it's backed up by this flash cache, up to 100 gigabytes per second. In less recent versions of Exadata, this was up to 50 gigabytes per second. So that is quite an impressive scan speed. Yeah, and then a very brief introduction into the in-memory stuff, which is very recent, rather new now, where Oracle adds with the latest version of Oracle 12.102, you get this additional optional in-memory column store that in principle keeps the data in a columnar layout, and the idea behind this is that it's really an additional cache. So you have the traditional row store still, and both formats, if you enable an in-memory column store, both stores will be kept in sync automatically by Oracle. So the row store and the column store are then synchronized. It's a true columnar store, true columnar layout. It takes advantage of these latest processor vector processing capabilities. It also comes with compression, and as you see, you also have this storage index technology. So this in-memory regions can also be skipped during these in-memory scans, and it can also evaluate these Bloom filters. So you see although these two technologies are quite different in the way they're actually implemented, they have also some similarities. And the basic point, the bottom line of these two technologies is that they both offer super fast scans. So it's a different approach in that sense that you have such a high speed of scans that you can get rid of many index-based approaches, and that is what both technologies have in common. One difference that might be worth to mention is that with the Exadata Smart Scan you have this additional CPU power in these storage cells, whereas if you have an in-memory scan, then everything happens on these compute nodes, as they are called in the Exadata environment, and which would be the normal host where the Oracle software runs if you do not have an Exadata. So the real-world case that this is all about here. So this was a very time-critical process, and as one key component of this time-critical process was a time-critical query, and it turned out to be an outer join between 20 tables. And of course, the one question might be, why would you want to do as part of a time-critical process a join between 20 tables? But that was the design at that stage, and the total data volume was 210 gigabytes that had to be scanned in these 20 tables. There were no reasonable index access paths available, so we were basically left with hash joins and full table scans. But what made this case here in first place look like an easy winner, like a very good case for Exadata, was that it turned out that out of these 210 gigabytes, there were only less than 1/10 of the data, approximately 18 gigabytes, that actually had to be processed in the compute nodes. So the majority of the data could be filtered out during these smart scans, because we only looked for approximately 1/4 of the data by filtering, and we only looked for 1/3 of the columns. So in total, that was really just a fraction of the total data volume. So we ended up with the so-called cell offload percentage that should you tell something about the efficiency of the offloading, which was higher than 90, greater than 90%, which looked really impressive. And we even had some physical clustering of the data. So this physical clustering means that we can benefit from this storage index technology. So given these theory and these figures, the expectations were quite high. So we have an Exadata environment. We can use this smart scan technology, which will basically process the majority of data in the storage cells already, and we just have a tiny fraction of data, less than 1/10, that needs to be processed in the compute nodes. Therefore, the expectations were like this should only take a couple of seconds, because we have this very high scan speeds. This was a so-called full rack Exadata environment where we should reach this very high scan speeds. And the result then actually was that the best runtime that could be achieved was then for this time-critical query 40 seconds, which was far slower than expected, although in absolute figures 40 seconds still might be not too bad. As I said, the expectations were quite different. And then of course the question was, what happened here? What was the why did we see these runtimes? Why cannot we really make use of these high scan speeds? You can see here this corresponds to an average scan speed of 5, a little bit more than 5 gigabytes per second, and even the peak scan rate according to this monitoring information was just approximately 28 gigabytes per second. Yeah, and just to give you an idea, we then started to run some tests, of course, to get a better understanding of what we can achieve on this platform, and what is possible and what is not possible. And the very interesting point here in this runtime summary is that these are runtimes in seconds, and you can see here runtimes between 2.5 seconds and more than 2 minutes. And all of these queries are actually based on the data that I've just specified. So each of these queries had to scan these 210 gigabytes, had to process this data that was then filtered and projected accordingly. Each of these queries performed the smart scan, so they're all based on the same data set. And in fact, of course, you can always come up with complicated queries that take long to process. But in this case here, these different results are actually from quite opposite queries. They are actually pretty simple and straightforward queries that still produce this vastly different runtimes, and I hope that it makes you curious enough to have a closer look at some of these queries in more detail, to understand how is it possible to arrive at such different runtimes if we, in principle, for each and every query have to do the same things in terms of data that we have to process. So yeah, that brings us to this part where we look at these different query profiles. And to give you an idea, what we used for testing was a little bit older. This is all happened some time ago. So at this time, this was an Exadata X28, which is not that reason anymore because we already have an X48. So this was an X28. This means you have two big compute nodes, each compute node with 64 cores. And we used only, for this test, we used only one of these compute nodes. So we had 64 cores in this compute node with hyperthreading, 128 CPUs, 1 terabyte of memory. This InfiniBand network and this full rack configuration means you have 14 storage cells with in total 168 cores on the storage layer, 5 terabytes of this flash cache, and the so-called high capacity disks. For Exadata you can choose between high performance and high capacity disks, but I think the most customers will choose the high capacity disks anyway because they're not much slower but offer a much higher capacity. And this environment should give us, on uncompressed data via flash cache, should give us a scan speed of 50 gigabytes per second. And we had another environment which was a more recent Exadata X38. In this case, both compute nodes were used in a rack configuration, so we had in total 160 cores, 4 terabytes of memory, this InfiniBand network, and also a full rack configuration, in this case even more and faster flash cache. So this is almost 45 terabytes of flash cache and also these high capacity disks. And of course it doesn't matter whether it's 5 terabyte or 45 terabytes of flash cache, the 210 gigabytes should be cached in both environments fully in the flash cache. And this is an environment that should give us this 100 gigabytes per second on uncompressed smart scans. So we started with a very straightforward, simple query, a select count star on a union all of these 20 tables, and these 20 tables already used the same predicates for filtering and the same projection as the original query. So we had to do the same kind of scans on all these 20 tables, and on top of this we did basically a count star just to see if we minimize the amount of work that has to be done outside this smart scan, what can we actually reach on this environments. And we tested this with different degrees, with parallel execution and so on, and I give you here only these results that ended up with the best runtime. And of course these segments were fully cached in this flash cache. And when we ran this simple query on the X28, we had a runtime of 2.5 seconds, and on the X38, 2 seconds, which gave us really quite impressive scan speeds. This means we were able to scan this 210 gigabytes on the X28 with more than 80 gigabytes per second, peak even 90 gigabytes per second, and even on the X38 we exceeded the 100 gigabytes per second, which of course then raised the question, how is it possible to exceed these 50 gigabytes per second, because the data was not compressed, it was uncompressed data, and then the question was, did we do something wrong? Are these machines simply faster than specified? And therefore we generated various reports for each query that should give us further insights into the query behavior and the runtime things that actually happened. And one of the nice things that you can do with an Exadata environment is you can use the session statistics to generate a very nice I/O profile that even allows you to look inside some of the activities that happen inside the storage cells. And it even allows you to understand how much data was exchanged between the storage cells and the compute nodes. And this is then here such an information on the I/O profile based on the session statistics. And one very convenient way of generating these session statistics reports is Tunnelboda's ExaSnapper tool, which is simple, which is a small PL/SQL script that allows you to generate such a report very easily. So what is this report supposed to tell us? It tells us that first, that from a database perspective, we really did 210 gigabytes of I/O. But it tells then also that this smart scan was capable of skipping most of the I/O, because this storage index safe tells us that more than 150 gigabytes weren't actually processed during the smart scan, but were simply skipped because the storage index technology told the smart scan, I do not even need to look into this storage region because the data that I'm looking for can simply be not contained in this storage region. So the storage index here worked very well. And we see also that a little bit more than 50 gigabytes then had to be really processed and were read via flash cache. We can also see that we didn't read anything from the spinning disks, so the caching really worked. It was read from flash cache. And we see some other interesting figures. It tells us that this smart scan only returned 4.5 gigabytes to the compute nodes. So out of this 210 gigabytes, only 4.5 gigabytes were then returned to the compute nodes for further processing. So this is almost an ideal case for this smart scan technology. Everything was processed in the cells and only a very tiny amount of data, even less than these 18 gigabytes that I specified in the beginning, were returned to the compute nodes. Why only this 4.5 gigabytes? Simply because Oracle was clever and understood that for the select count star, it simply needs to ship the row IDs rather than the actual column values to the compute nodes, and therefore it was even less than this 18 gigabytes. And another important figure that we will see later on, it will become more important, is that we can see that the same amount of data, this 4.5 gigabytes, was then exchanged between the compute nodes and the storage cells. So probably the reason why we were able to achieve such high scan speeds is the point that the storage index technology allowed the storage cells to skip the majority of data and do not perform any I/O at all in those storage regions. And in order to confirm that, we did another test, but before I come to that, I wanted to show you two other profiles. This is the relative activity profile on the compute nodes, which tells us that 2/3 of the time where the parallel slaves on the compute nodes were actually waiting for input from the smart scans, and only 1/3 of the time we've spent on CPU in the compute nodes. And in absolute figures, this means approximately 1 minute of CPU time, because it was parallel execution. We had many parallel slaves active at the same time, so within this 2.5 seconds we spent 1 minute on CPU and 1.5 minutes waiting on I/O, which gives us in total 2.5 minutes of database time that this statement spent in the database. Then we did the same test again, but disabled the storage indexes just to see whether this confirms that we exceeded these specified scan rate. And we can see here that with the storage indexes disabled but doing exactly the same query, the runtime increases here from 2.5 to 5 seconds on the X28 and from 2 to 3 seconds on the X38. And this gives us a more realistic view on these smart scan throughput. So we are now below this 50 gigabytes here on the X28 and below the 100 gigabytes on the X38. And we can see this confirmed in this I/O profile. Now we can see that nothing was saved via the storage index. We had to process all the 210 gigabytes, and we can see here that almost everything was read via this flash cache. And it looks like if the flash cache is saturated, then the storage cells start reading from the disks concurrently to support the I/O. And the remaining figures remain the same. We still this smart scan still returns this 4.5 gigabytes, and the amount of data exchanged is also 4.5 gigabytes. So the only difference is now that we no longer benefit from this storage index technology, and therefore the scan simply takes a little bit longer, which is also reflected in this here. So we see now the parallel slaves wait most of the time for this smart scan to return these row IDs, and we do not spend in relative scene on CPU. We can see here we still, in absolute figures, we still spend the same minute on CPU, but we now, instead of 1.5 minutes, we spend almost 5 minutes waiting for I/O, which then means that we in total approximately spend 6 minutes on the compute nodes when running this query. Now the next level of complexity for these queries was then, instead of a count star, we ran the same query but did a max on each of the columns that were used in the original query. And you can see here that in this case the storage indexes were enabled again, so this has to be compared with the initial query runtime. So we have an increase from 2.5 to 7 seconds on the X28 and from 2 seconds to almost 4 seconds on the X38. And you can see also the corresponding scan rates were then lower than before. And looking at this profile, we now see the only difference. We still have the same things here above. The only difference is now that we, instead of these 4.5 gigabytes, we now have to return these 18 gigabytes from the storage cells to the compute nodes, and the same amount of data is exchanged between those two. What also becomes obvious is now that since we have to do a more complex operation on the compute nodes, which is this, instead of count star, now this maximum value, which is not too complex, but it's more complex than a count star, we spend more time on CPU and wait less on the I/O. So this is already a trend that we can see here, more time spent on CPU in the compute nodes, which also is reflected here. So CPU time now increases from 1 to 5 minutes, and the I/O wait time, interestingly, maybe due to the higher amount of data that needs to be exchanged, also increases from this 1.5 minutes to 2.5 minutes, which gives us in total 7.5 minutes of database time. And now we come to this original query, which is in principle the same query, but this time we do a join instead of a union all. And of course, a join is a more complex operation than a union all, but the sharp increase in runtime is still maybe a little bit surprising. So we go from 7 seconds to almost 40 seconds on the X28, and from 4 seconds to 24 seconds on the X38. So that's quite a significant increase in runtime. And the question is now, of course, what in detail, what is causing this sharp increase in runtime. And when we look at the I/O profile, then this looks quite different than before. And before I come to these figures here above, I want to focus on these figures here first, because the important point is, for this query, we still do the same smart scan. So we still do this smart scan on this 210 gigabytes. We still benefit from the storage indexes. We still use the flash cache. And the smart scan still returns this 18 gigabytes. So this is still the same. So the basic profile of data that needs to be processed from an I/O perspective is exactly the same as before. But as you can see, the main difference here is, from an I/O perspective, that we now have to process 60 gigabytes, almost 60 gigabytes more of data in terms of I/O. So instead of 200 gigabytes, we have now 270 gigabytes. Why? Because we read 30 gigabytes more, and we even write 30 gigabytes more. And since this is a query, it's very likely that this is caused by temporary I/O. And we see another interesting effect here in terms of I/O that happens on the storage layer, since this temporary table space is mirrored with this normal redundancy ASM mirroring. These 30 gigabytes of writes here from a database perspective turn into 60 gigabytes of writes. And what is also obvious, that these temporary I/Os are not taking place in the flash cache, but they're taking place on the spinning disks. So in total, we have now here, for this query, due to this temporary stuff, we have now 90 gigabytes additional I/O that takes place on the spinning disks. And you can also see this here reflected now in this volume that needs to be exchanged between the compute nodes and the storage cells. Since these 90 gigabytes also have to be transferred between compute nodes and storage cells, so read and write activity. We have 90 gigabytes more that need to be exchanged between compute nodes and storage cells. So this means instead of 18 gigabytes, we now have almost 110 gigabytes that need to be exchanged. And that makes already a very good point here that depending on what you actually do with your query, these smart scans might become less relevant because we still have the same smart scan profile, but we have additional activity. We can see this also reflected here, that we now spend time on this temporary reads and writes from a compute node perspective. But what is also interesting, that we even spend more time on CPU than before. And if we look here in absolute figures, this means we jump from, I think it was 5 minutes CPU time of the previous query, we jump now to almost 40 minutes of CPU time, and 2.5 minutes I/O time to almost 16 minutes I/O time, which results in a total DB time of 55 minutes. So that is quite a sharp increase, in particular not only in I/O time but in CPU time. And looking at this corresponding real-time SQL monitoring report, it becomes obvious that there are a couple of operations on execution plan line level that seem to be responsible for this increase for the in CCPU and also in terms of temporary I/O. So one thing that becomes obvious here from this is that we have here this so-called hash join buffered, and below and above we have these non-buffered hash joins, and it seems to be these hash join buffered are a problem in terms of I/O, because these are the two operations that cause this additional spill to disk. So each of them spills 16 gigabytes to temp. So these 15 gigabytes have to be written and read again by these operations, which explains this 30 gigabytes in total read and write additionally. But what is not so obvious from this snippet here of the report, that these operations are also responsible for some significant CPU consumption. So these operations not only cause additional I/O, they also consume significant CPU. And also these send and receive operations here that I have highlighted, these are also taking in summary, because we have many of them, because we have that many joins here, these 20 joins. We have many of these redistributions for the parallel execution. These are also taking significant CPU time. So yeah, that is interesting, and the reason for these hash join buffered is that there is a limitation in this parallel execution implementation, that only one of these redistributions is allowed to be active at the same time. In order to avoid and to prevent this from happening, Oracle has to buffer the data temporarily, and this is what these hash join buffered are about. So they have to do more work than these regular hash joins, and this explains this additional CPU and I/O consumption. And since it was then the question, how much really does these these hash join buffered influence the runtime, I created an artificial test case. This is something that you cannot really do with your real life queries and real life data, but with my artificial test case, I was then able to influence the number of hash join buffered that take place during this query. So I could either have none of these hash join buffered, or each of these hash joins could be a buffered hash join. And I did some additional tests, and by simply eliminating these 2 out of these 20 hash join buffered, the runtime of this query was then 23 seconds instead of 40 seconds on this X28, and 13 seconds instead of 24 seconds on the X38. So simply by eliminating these 2 hash join buffered, I almost halved had half of the runtime. So that's quite a difference, and makes obvious that these hash join buffered are really a threat to the performance, because they take so much longer to process. But as I said, there is no direct way, in a real-life case, there's no direct way of telling Oracle, I do not want hash join buffered. Due to this limitation, Oracle simply has to add these buffered hash joins and you hash. And the only way you can influence this is indirectly by changing these so-called parallel distributions. And I will come to that point later. And if we look at the profile of the I/O, if you look at the I/O profile, we see all these additional I/O is gone, and we have again this very nice and clean picture, and this explains to some degree why this is so much quicker. But another interesting point is that we become more and more now CPU bound with this query. So we now spend almost all of our time in the compute nodes on CPU and do not wait a lot on these smart scans. But the main difference here is then that we have eliminated this I/O wait time, so we are again back at this 2.5 minutes I/O wait time, but we also almost saved 20 minutes of CPU time, and that is even more relevant to the overall runtime than saving this temporary I/O. So if I now do the opposite and you use this worst case scenario where each of these hash joins is a hash join buffered, you can already see that we then it takes, even on this Exadata platform, more than 2 minutes on this X28 to perform this statement, and almost 80 seconds on the X38. So, and this shows that with these maximum number of hash join buffered, there is a lot of additional work obviously going on. And looking at the I/O profile, this is confirmed. We can see here in this area we still have this basic same query profile. So we still have this smart scan, we have this flash cache, we have the storage indexes working. The smart scan returns still this 18 gigabytes, but as you can see from this graph here, this is almost no longer relevant for this query because we do an additional 300 gigabytes of I/O. We have to read 150 additional gigabytes, write additional 150 gigabytes, and it turns out, of course, on disk, due to this duplication, the mirroring, that we have 450 gigabytes of additional I/O in this case on disks in the storage cells, which also means that we need to exchange an additional 450 gigabytes between the compute nodes and the storage cells. So this temporary stuff is really bad for Exadata, is bad in general, but particularly bad for this Exadata environment because it makes these smart scan technology less relevant. We can see this also confirmed in this year. We spent 45% of time on this temporary I/O and still even more than 50% on CPU. And yeah, the absolute figures are then also quite impressive. 1 hour 45 minutes on CPU and more than 1 hour spent on I/O, which gives in total almost 3 hours of database time. Yeah, so these were some of these different results that we had, all based on the same basic data set and just different ways of processing the data. And then the question is then, of course, what can be done if we really want to perform such a complex or more or less complex join operation? Is there anything that can be done to optimize this? And obviously what needs to be reduced is the CPU time that we spend on the compute nodes and the I/O time that we spend on the temporary I/O. And then what I did is, although this test environment was configured to use half of a terabyte of PGA with this PGA aggregate target configuration, Oracle still decided to spill to disk. So the only way, without fiddling with any undocumented underscore parameters to influence this automatic PGA management, was to switch to the traditional manual PGA management using the sort area size and hash area size parameters. and by doing that I could reduce the runtime from these 2 minutes, more than 2 minutes, to 70 seconds on the X28. So that is more than 50 seconds saved, so more than 50 seconds faster. That's quite impressive. And if we look at the profile here, at the I/O profile, we can see this confirmed. These 300 gigabytes additional temporary I/O are gone. We still have these 20 hash join buffered, but no temporary I/O, so that's fine. But we now see that this query is now completely CPU bound on the compute nodes. So we, although we do this smart scan, we spent 96% of the time on CPU on the compute nodes, which is also confirmed here. So we can see that we have not reduced the CPU time significantly. We still have almost 1 hour 45 minutes of CPU time, but the I/O time is reduced. So now the question is then, of course, can I somehow reduce the CPU time, which is here taking almost 100% of the processing time. And we did then a test with partitioning the data accordingly. So according to these join conditions, we did hash partitioning, or in this case even hash sub-partitioning, and the results were quite impressive. So instead of 40 seconds, 20 seconds, or even more than 2 minutes, we were now down to a runtime of 15 seconds on the X28, and also corresponding scan rates, at least peak scan rates on the X38, 7.5 seconds for the same query. So that is a pretty significant difference. We can see that here confirmed. We have again this nice I/O profile, which looks a little bit different because we have a different physical layout now with the hash partitioning, but in principle it's the same as before. And what we still see is that we are more or less CPU bound on the compute nodes, but the main difference, of course, is now that we have reduced the CPU time dramatically. So instead of spending 40 minutes or whatever for the other queries, we are now down to 13 minutes CPU time and just a couple of seconds of I/O wait time. So that was quite a big difference, and the reason for the difference is that these partition-wise operations in this case allowed two things. First, they do not require to redistribute the data because the data is already suitable in a suitable way partitioned, so there's none of these px send and receive operations required. And more importantly, as a side effect of these missing redistributions, no hash join buffered took place. So this buffering of these joins was also gone, and very likely these partition-wise joins are also a little bit more CPU efficient in general because these so-called hash tables are a little bit smaller than for the hash join that has to work on the full data set. Because the partition-wise join, as the name suggests, can simply work partition by partition and only has to build hash tables in the size of each partition. So the lessons learned from this exercise and this analysis was that these scans can really be very, very quick, as we saw, these smart scans and the memory scans. I will come to that in a moment. Offer really super fast scan speeds. We have seen scan speeds exceeding these 100 gigabytes per second on uncompressed data, which is really impressive. But depending on what you actually do, you simply might be moving from one bottleneck. By reducing one bottleneck, you might simply be moving to the next one. And SQL execution can spend significant time on non-scan activities, and this is exactly what happened to us in this particular case here, that the SQL execution time was then dominated by non-scan activities. And if you have such a profile, then the net effect of the superfast scans might simply become less relevant because all of your time is spent on other things than doing these scans. So by making these scans so fast, we then had the problem that we had other activities that took the majority of time, and yeah, therefore the overall scan speed was in this case far lower than initially expected. And this is also the reason why I have mentioned here this in-memory scans, because if you look at the query profile like I showed you before, if for instance 95% or even more of the time is spent on CPU in the compute nodes in an Exadata environment, then it doesn't really matter how fast your scans are, even if the in-memory scan variant that I couldn't test for this particular case here, even if the in-memory scans were faster than the smart scans, it wouldn't really reduce the runtime. So for this particular case here, an in-memory scan wouldn't make these queries, at least those that were so CPU intensive, wouldn't make these queries any faster. And it could be even argued, it could even be possible, and it's not unlikely that these in-memory scans would even be slower than the smart scans, because as I said in the beginning, the in-memory scans would have to be performed by the same CPUs that do the non-scan activity. And since I was already CPU bound with non-scan activities, it could even happen to me that using in-memory scans I become slower, because these in-memory scans have to use the same CPUs, whereas the smart scan technology allows me to take advantage of the additional CPU power that I have on the storage cells. So I'm not entirely sure that in-memory scans would have even made this here in any case faster. Maybe it would have been even slower than this smart scan case. Yeah, and just a couple of examples. This is not a list, a full list of things that might be activity that is outside of scanning, but in this case here we had hash joins. Hash join buffered are particularly bad. The temp IO was a bad thing, and these redistributions were all activities outside the scans that influenced the overall runtime significantly. But there are other activities possible, like aggregations and other stuff that you might have in your query profiles that take a lot of time. And in this particular case here, we could really make things faster via this partition-wise operations. They can allow to minimize the overhead, but not necessarily, of course, in every case. They are not always applicable. Partitioning comes always with pros and cons. So this is something that needs to be well thought of. Well, you have to think through whether this really gives you the advantage and whether it works in your particular case. In this case here, in this particular case, it was really pretty helpful and made things a lot faster. And therefore, to wrap things up, even in those with those super fast scans, you probably still need to think about the design. Simply throwing things at this system and thinking it's so fast it simply can cope with everything. This is true, but you might have then the situation that you do not really make the most out of these environments, and therefore that was also one of the conclusions. It certainly makes sense to still put more effort into the design of it. So, and I think that's it from my side, and I would then hand over to Amy again.
Hi there, can you hear me?
Yep.
Hi there, thank you very much. That was great. I think we've had some really good feedback so far, and people finding the session really interesting and really useful, and already requests for the a recording of it and the slides. So, like I said, we will be forwarding that round to everyone in the next few days. But just to check, Randolph, can you see the questions now?
Actually, no. I still have only the chat window and the attendees window, but I do not see any questions.
Right, okay, bear with me one sec. What I'm going to do, if I just take over this screen, and then you'll be able to see my screen. Okay. Okay, can you see my screen now?
Yeah, I can see your screen, yeah.
Okay, so can you see the questions on there?
No.
Right, okay, what I'm going to do then, let me just read out a couple of questions for you if that makes, things easier. Okay, cool. So the first one from Kevin is, could you fairly compare SAP HANA, I think it is, and Exadata in terms of in-memory operation? So that's SAP HANA.
Yeah, well, I think the point here is that SAP HANA is a true in-memory database, whereas Exadata per definition is not really an in-memory database. Exadata, as I outlined in the beginning, is this engineered system which comes with this secret sauce, with this special smart scan technology. Of course, you can use this new in-memory option, which has been added in the latest version from Oracle 12.102 on. You can use that on Exadata as well, but apart from that, you cannot really directly compare Exadata with SAP HANA, because HANA is really a true in-memory database, and I think there are some significant differences. I think, for example, in SAP HANA you really have to keep all of the data in memory, so it's a in-memory database only, whereas with this new in-memory column store in Oracle you can selectively have some of your columns of your tables, some of your tables, maybe some of your partitions kept in memory in this in-memory column store, but you always have this traditional row store in addition always there. So there are some key differences between this SAP HANA and in-memory column store.
Okay. So the next question, we just had Atul asked whether the query, the first query you showed, was the first time on this Exadata, or the data was already cached by earlier runs?
Yeah, that's a very good question. All of these results that I've shown were the best results after running the queries for a couple of times. So as I said in the beginning, the basic principle was that all of the data is already cached, and in this cached via the so-called flash cache, and yeah, so the runs were then performed with this data already cached, and we did of course always do a couple of runs and then did an average to show then these results here. So yeah, it was all cached. Yeah.
And then I've just had one from Sunir that says, what about the combination of in-memory with smart scan? And then he put means 12C in Exadata.
Yeah, that's also a very good question, because as I tried to outline in the beginning, these are actually two different technologies that aim for the same. So you have an Exadata which already has this smart scan technology which offers this super fast scan technology, and now you have in addition, of course it costs also in addition, so there's an additional license that you have to pay for this in-memory stuff, but if you pay that then you can have both on Exadata. And it's probably not that trivial to understand for which purpose you might want to use which of these super fast scans. There are some differences. For instance, for example, this in-memory scan is probably not so good in supporting queries that query very wide tables, and if you query a lot of columns from these tables, then the in-memory technology probably loses, and the Exadata smart scans can very well support smart scans on very wide tables. So this, for example, might be one case where the smart scan technology can outperform the in-memory performance. But as I said, it's probably a question that many of the Exadata customers have. So now that they have maybe both technologies available, they are quite different in terms of implementation, but the overall goal is the same. They try to offer you this super fast scan technology, and yeah, so there's a bit of, you could say, competition between these two super fast scan technologies, and yeah, it probably is then a good question which technology to use for which purpose.
Okay, great. And then we're just about out of time, but there's just one final question from Alexander, who's put, it probably isn't fully related to this webinar subject, but what is the difference between storage indexes and zone maps? It seems the same stuff. Could zone maps help in your case?
Yeah, that's also a good question. The zone maps technology is something that is new in 12c, and in fact it's more or less the same than storage index, so it has exactly the same purpose. It allows the scan to skip certain regions because the zone map allows to tell that this region of storage can simply not contain the data I'm looking for. And the main difference is that zone maps from 12c on are unfortunately also only supported on these engineered systems. But the main difference is that the zone map is something that you define yourself and is is basically something like a persisted information, so it takes additional disk space and is an object in your database which represents the zone map information, and you have the control over this zone map, which columns should be covered by the zone map and so on. Whereas the storage index technology has exactly the same purpose but is automatically maintained by these storage cells on Exadata, and also in the in-memory part is automatically maintained, and you do not have direct control over which columns will be covered by these storage indexes. And that's probably the main reason. But the idea behind these zone maps is exactly the same as the storage index, and well, they probably could have been used in my case here, but this wasn't 12c yet, so I couldn't use zone maps in first place. And secondly, since they do the same as the storage index, I think the query performance would have been pretty much the same, so it wouldn't have changed anything then. Yeah, so that's it.
Okay, and I think that's it. So thank you very much. Thanks to you, Randolph. And to my colleague, Richard. Yeah, it's been great having you. Really great session. Thank you very much. Yeah, as I mentioned, we'll be once we've downloaded the recording, we'll be sending that round to everyone via email. If there's any questions we've had which we haven't managed to get to, we'll forward those on to Randolph, and I'm sure that he will contact you with an appropriate answer. But apart from that,
sure.
Yeah, it's been great. Thanks everyone for joining us, and hopefully we'll see you next time.